Okay, I have a fresh cup of coffee and I'm ready for another problem. And in this problem, I have the proposition if A, B, and C are sets, then A minus B and C is equal to A minus B or A minus C. And here I'm going to try to prove that this is true. Okay, so if you're unfamiliar, sets are kind of like a list. So a set, let's say set A, it could just be like letters, or it could be numbers, or it could be grocery, or a combination of things, like a grocery list or anything. So a set's like a list. And order doesn't matter. I wrote those in order, but order doesn't really matter with sets. But we don't write duplicates. So there's some rules there, but hopefully you at least know what a set is now. Okay, so from there, how do you even prove something with sets? And really, you start with if an element or an item is in this set, then da 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 da. That's how you're going to start. So what I'm going to do is if some element A, like the letter A, is in this, then it's got to be in this. And that's really how you prove it. And if this was subset or something, then we prove that it was subset. But in this one, it's equals, okay? The equals is going to do something to me where I have to go twice, okay? So I'll get to that, but let's get into it. So proof. Let's try to write a proof of this. Again, with sets, usually what you do is you say, okay, well, suppose that some element A, lowercase a, we use lowercase for elements to note that it's not another set. So suppose that the element A is in this. Okay. So if some element A is in here, then therefore it must be in here. That's what I'm going to try to do. Okay, well, it's going to take me a few steps to do it, but let's see. Then, if this is true, then what I'm going to do is I'm going to try to break this apart. I'm going to break this into its pieces. Like in algebra class, we would, we'd do different operations, okay? One thing I want to note, and I find it easier to work with, so note, I'm going to switch notations on us here. If we have something like A minus B, that's the same thing as A intersect B complement. So in the textbook that I use when I teach this class, or classes like this is the notation they use. These are equivalent notations. It's just another way to write it. However, I kind of want to use this notation for the next step here. So I'm bringing it up for that purpose. So A is an element of A and B and C, and that's the complement. Okay, so not this. That's what the subtraction. So what I've done so far is I've just removed the subtraction piece. That becomes and that becomes complement. Okay, that's just a notational thing. That's nothing serious, but that's what's going on there. Now, what I like to do with these proofs is I like to break it up with replacing this with the word. And also notice that we have the complement here, and I'm probably going to have to do something with that in a moment. So then A is an element of the set A, and A is an element of B and C complement. Okay. All right, now with this, I want to break this into pieces. This is good. This is about as fundamental as I can get it. But over here, I want to break this up. And like a lot of math problems, there's math problems inside it. And so what I'm going to do is I'm going to call upon my friend DeMorgan. I'm going to phone a friend. I think that's how you spell his name. And it's kind of like distributing the complement. So what's the opposite of B? B complement. What's the opposite of the intersection? The union. What's the opposite of C? C. Okay, those are equivalent by De Morgan's law. All right, so I'm gonna use that, and that's gonna help me break things up. Okay, that way I don't have these parentheses anymore. Just like in algebra, when we try to break things up, getting rid of those parentheses, and that's what we're doing in the sets too. This was supposed to be and A is an element of B complement, or A is an element of C complement. Okay, so I broke that up. Okay, use my friend De Morgan to help me that. All right, so now what can I say? Well, I could say that A, like as in the element, is in A and A is in B complement, or it's in this and this. So I'm going to do that. Then A is in A and A is in B complement, or A is in A and A is in C complement. Okay? Now, I know full well where I'm going. Okay? So I'm kind of looking up here and thinking about how I'm going to get there. All right? But so far I'm just breaking things up. Now, it helps if you know the notation and you know the tricks. But so far I haven't broken any rules. Okay? Now, I've broken everything up in as much pieces as I can. Now I'm going to start putting things back together. So if that's true, then A is an element of A and B complement. Or A is an element of A and C complement. That has to be true. Okay? But really, what am I doing? I'm just starting to switch the notations back. That's all I'm doing. Next up, I think I'm going to fix this or, and I can kind of consolidate things. So I'll put this or into the union symbol. So then A is an element of A and B complement, or the set A and C complement. Okay. Now again, this was just a notational thing. A minus B is equivalent to A and B complement. So going back up here, then I can just switch the notation back to what it was. Then A is an element of the set A minus B, or A and C complement. Whoops, I did the exact thing I didn't want to do. I meant to do minus C. I'm going to rewrite it. So that line was a dud. Then A is in A minus B, A minus C. And that's exactly what I was trying to show up here. Okay, does that mean I'm done? Well, I wish it did. But what I really have shown is thus A minus B intersect C is a subset of A minus B, A minus C. When you're proving things, it's rigorous stuff, okay? So the only thing we've shown sorry, my phone was alerting me that it's low on battery, but the only thing we've shown is that this is a subset. I have not proven that these are equivalent, okay? So if you want to prove that something is equivalent, you have to go both ways. So the next step is to show, and I'm going to set my paper up so I can keep going. I think that'll work. That should be fine. Okay, so the only thing I've shown is that the left-hand side was a subset of this. I haven't proved that these are equivalent statements. So, once again, suppose A, and you can pick any lowercase letter you want, or symbol, or it's your proof. With me, I'm just going to pick the same. So, just It's almost like a whole nother proof. Suppose A is in A minus B union A minus C. So here I'm just starting over on the right-hand side, okay? So what would happen there? All right, I'm going to do the same thing. I'm just going to break it up. So if lowercase a is in here, well, then A is in A and not B, A and not C. All right, I showed that before, the switching of the notation, but I find it helpful. Well, then A is in A and not B, or A is in A and C complement. That's easy to see. We can break that up too. A is in A and A is in B complement, or A is in A and A is in C complement. And it's really easy to see how you can start switching things back up. If this part made sense, then fixing the second part is really easy. Okay. All right, so how can we do it? Now we've broken everything up into different pieces, so we can kind of move them around. I mean, it has to be mathematically true, but I can kind of move them around as we please at this point. So I could say that it's true that if all this is true, then A is in the set A and A is in B complement, or A is in C complement. That has to be true. Okay. Next line, A is in A and A is in, how can I put these together? Well, I could say B complement, let's just do the union, C complement. All right, well, do you remember my friend De Morgan? Well, De Morgan says that you can kind of like factor out the complements there. Okay. All right. We're really close now. Okay, well, if that's true, then A is an element of the set A and the set B and C not, or B and C complement. All right, well, if you'll let me just switch back to the original notation, then A must be within the sets A minus B and C. So I'm switching the minus sign for the complement sign, and that's equivalent. Okay, so then, what did I do? I showed that A minus B or A minus C has to be a subset of A, B, and C. So that has to be true by this line. All right, well, since the previous step, I showed that this has to be a subset of this, and then I showed it the other way, well, this has to be a subset of this, and you can kind of think about it almost as simple as like, well, if 5 is less than or equal to 5, and then you switched it around, 5 is less than 5, well, then that's 5 equals 5, right? That's a silly example, but it's true with sets too, right? So if it's a subset of each other, it must just be the same thing. So I ran out of space, but this is the big thus. A minus B and C equals A minus B or A minus C. All right. I'm going to put a little box for proof, end of proof. Okay. So that's kind of cool, and hopefully you got something out of it with seeing how we're taking De Morgan's law. That's important to know, the different versions. Sometimes I use the switch of notation at my disposal, so there's a lot of things going on with these proofs. But that's how you can prove if they're equal to each other. And really, generally in math, I don't have time for a tangent, but generally in math, if you see if then, if and only if, you're going to have to prove that going both sides. So if you see something like if and only if, you got to prove it both ways. And if you see something equivalent, that are equivalent, you should prove going both ways, that that is the only way that that can happen. Okay? Hey, I hope you got something out of it, okay?